You can see these two motors here. Both are different in size and each has a 4-wire connection. Now, how can we determine which one is a single-speed motor and which one is a double-speed motor? Additionally, can we exchange these motors? For instance, can we install a double-speed motor in place of a single-speed one, or vice versa? Let's find out if that's possible. I'll give you the answer right away. Yes, it's possible. But how? That's what I'm going to explain to you. In today's video, I will show you 3 methods to identify what type of motor this is. If I want to exchange these two motors, the first thing I need to know is their function. Is it a double-speed motor or a single-speed motor? And what specific functionality does it have? If there's a sticker on the motor, it's easy to figure this out. But if the sticker is missing, how can we identify it? For that, we need to understand the internal winding of the motor. I will also explain how to determine whether it's a single-speed or double-speed motor. Now, what we'll do is take one of these motors and test it. Even though I already know which motor is double-speed and which one is single-speed, I'll pick a motor that even I'm unsure about, so we can learn step by step together. Let's take this motor, test it, and also look at its diagram to understand how it works. Now, we'll test this motor step by step and note its readings along the way. I'll explain which motor it is as we proceed, making it easy for you to understand. First, we will set the multimeter to resistance mode. We'll take one probe and connect it to the brown wire and then test it with the black wire. Let's see what reading we get. The multimeter shows 139.8, but we can round it off to 140 ohms. So brown and black wires are 140 ohms. Next, we'll test brown with the red wire. The multimeter shows 274.7 ohms, so brown and red, 274 ohms. Now we'll check brown with the white wire. The multimeter shows 0.3 ohms. This means brown and white wires are 0 ohms. The 0 ohms reading indicates no resistance, which means there is no coil present between these two wires. Just two wires directly opposite each other will not show any resistance if these wires are joined, as there's no coil present. If a coil exists between them, resistance would be detected. This means the brown and white wires are directly connected without a coil, indicating that these two wires are common wires. So, based on this, we should be able to find 3 combinations in total. Let's proceed to identify the third combination to complete our testing. Now let's check the red wire. First, we'll test red with black. The reading shows 135.3 ohms. Red plus black equal 135 ohms. With this, all the combinations are complete. The fourth wire is the common wire, so it doesn't play any active role beyond being a shared connection. From this, we can conclude that this is a single-speed motor. Next, I'll draw its internal diagram for you to show how the components are connected and how it functions internally. Here's an important point to note. Whether it's a single-speed, double-speed, or triple-speed motor, all of them have 2 windings in common, known as the running winding and the starting winding. So regardless of the speed, these 2 windings will always be present. Since we're working with a single-speed motor, we now need to identify which wire corresponds to which winding and where it is connected. To do this, we already have a complete procedure and have checked the values. When you analyze the readings, the highest value indicates the total resistance across both windings combined. In our case, the highest value is between the brown and red wires, which is 274 ohms. This value represents the sum of the resistances of both windings. This means the brown and red wires are connected to the ends of the coil, and their combined resistance includes both windings. This confirms that these 2 wires are common points for the windings. Now that we've identified the brown and red wires, the remaining wire is black, which is our common point. We're left with 2 wires, and now we need to figure out where they are installed. The lowest resistance value always belongs to the running winding, which connects to the run point of the motor. From our readings, the red and black wires have the lowest resistance of 135 ohms. This means the red wire is connected to the running winding or the run point of the motor. The medium resistance value is between the brown and black wires. This resistance corresponds to the starting winding. Therefore, the brown wire is connected to the start winding. This step-by-step process makes it easy to determine the connections and how to install them properly. Here, a capacitor is installed between the start winding and the run winding. This helps in the motor's operation by providing the necessary phase shift. It is also crucial to correctly connect the line and neutral wires. Otherwise, the motor may overheat. Here's the proper procedure. 1. Connect the live wire to the common point, black wire. 2. Connect the neutral wire to the run point, red wire. By following this method, the motor will operate efficiently without overheating. Now that we've completed the single-phase, single-speed motor, let's move on to the next motor, which is a single-phase double-speed motor. This motor also has 4 wires, but we need to determine how the double-speed functionality works. I'll explain step by step how to identify which winding is for low speed and which is for high speed, and how to test it properly. Stay tuned as I demonstrate the process. I've redrawn the diagram to make it clearer, and I want to address an issue you might encounter. The principles I explained earlier remain the same and cannot be changed, but sometimes, while applying them, things might not align as expected. If this happens to you, it's important to understand why. For example, when we look at the motor's diagram, it appears different. Here's what happened. I connected the red wire to neutral and the brown wire to the start point. According to the principle, brown and white are common, so the brown wire should connect to the start winding. But in this case, its combination with neutral doesn't seem to fit. This discrepancy occurs because of the internal design of the motor or how the connections are configured. I will explain this further so you can understand it clearly and apply the correct solution. Stay with me, and everything will make sense step by step. Here's what happened. The company provided a wiring diagram where the black wire is installed as the main connection point. The diagram shows an electrical symbol between the white and black wires, indicating power flows here. The brown wire and red wire are connected to the capacitor, which means the red wire is designated as the starting wire. While this setup is correct based on measurements, the company likely made these changes to adjust the rotation direction. If the required rotation isn't achieved, the company swaps the connections, placing the red wire on the start point, the white wire with neutral, and the brown wire with the capacitor. This small adjustment ensures proper functionality while maintaining the overall wiring principle. Let's analyze the double-speed motor step by step and identify its combinations and resistance values. This motor has 6 possible combinations, and we'll measure the resistance for each pair. 1. Black and pink. The measured resistance is 47.1 ohms, so we'll round it to 47 ohms. 2. Black and blue. The measured resistance is 83.6 ohms. 3. Black and orange. The measured resistance is 96 ohms. 4. Pink and blue. The measured resistance is 130 ohms. 5th, pink and orange. The measured resistance is 142 ohms. 6. Blue and orange. The measured resistance is 178 ohms. By recording these values, we can now analyze and determine the configuration of the motor's windings and identify which wires correspond to the low-speed winding, high-speed winding, and the common point. Let's move to the next step to figure this out. Now that we have the resistance values, the next step is to figure out the purpose of each wire, where it is connected, and how it operates. This is a simple process if you understand the principle that every motor has a starting winding and a running winding. I will also write it on for better understanding for wire connections. To adjust for high and low speeds, an additional resistance is added, meaning another coil is installed in the motor to create a difference in speed. Now, how do we determine which wire connects where? For this, we need to analyze the resistance values, though the process will be slightly different. The principle remains the same. The highest resistance is between blue and orange, which means one end is blue and the other end is orange. However, we still don't know which wire corresponds to which side, so we'll need to dig deeper. As I mentioned earlier, the running winding always has the lowest resistance, while the starting winding has a higher resistance. The second highest value will correspond to the starting winding combined with the additional coil. This is because the shorter winding combines with it to create the resistance value. The second highest resistance is between pink and orange equals 142 ohms, which indicates that these wires are connected to the starting winding and the additional coil. At this point, we still don't know exactly which wire connects where, but using this method step by step, we'll figure it out. Looking at the blue and orange combination, we can see that these are the common points in this setup. Then, when we check the pink and orange combination, one side is pink and the other side is orange. Since orange is common to both, this means orange is the starting point because it connects with both pink and blue. Orange is common to both pink and blue, making it the central reference point in the circuit. 2. Pink and orange combination. The pink wire corresponds to the starting winding as it forms the second highest resistance with orange. 3. Blue wire. The blue wire represents the running winding. Final conclusion, by analyzing these 2 points, now that we've identified 3 wires, the question arises, where does the 4th wire come from? It's a matter of common sense. Once the 3 wires are identified, the remaining wire will naturally be the black wire. This way, we've determined all the wiring connections. Understanding with resistance values. If things get more complicated, you can rely on the fact that there are 3 coils in the motor. The process to identify the wires is as follows. The pink and black combination has the lowest resistance. This corresponds to the starting winding. The black and blue combination has the next lowest resistance, which matches the running winding. The black and orange combination shows 96 ohms, which is in line with the principle and represents the additional coil for speed adjustment. If a double-speed motor burns out and you cannot find a replacement, you can install a single-speed motor. Here's how it works. The PCB in the system has 2 relays, as it controls 2 speeds, high and low. The line wire is common to both relays, and each relay has a separate output. When the PCB turns on, it activates one relay while keeping the other off. If the high-speed relay is on, electricity flows to the high-speed winding, and the fan runs at high speed. If the high-speed relay turns off and the low-speed relay turns on, the resistance increases in the circuit, reducing the speed of the fan. By understanding this principle, you can connect the single-speed motor to the high-speed relay's output and bypass the low-speed relay, ensuring the system operates smoothly. Now let's discuss how to install a single-speed motor in this setup. Since a single-speed motor doesn't have the additional coil for speed variation, one point on the PCB will remain unused. When the high-speed relay is on, the fan will run at its single speed. However, when the low-speed relay is on, the motor won't operate because it doesn't utilize the extra coil. To fix this, you need to connect both relay outputs together on the PCB. This way, regardless of which relay is active, the fan will always run at its single speed, ensuring the unit doesn't stop and operates smoothly. If the system changes and you have a double-speed motor, but the single-speed motor is burnt out, installing the double-speed motor is simple. Since the system was designed for a single-speed motor, the PCB will have only one relay, but the double-speed motor will have 2 coils. To install it, connect the high-speed wire of the double-speed motor to the existing relay. Leave the other wires unused in the system. This way, the fan will run at high speed without any issues. Now, let me show you that the wiring diagram is the same. In this setup, orange is at the top common point. Blue and black are connected to the line and neutral. Red is the wire for speed control. This confirms that the principle remains consistent and correct. The difference with the previous motor is simply that the company changed the wiring arrangement to adjust the rotation direction. This change is specific to the motor's design, but the overall principle and functionality remain the same. Click on the left or right thumbnail to watch our next videos, and subscribe. Thank you.